So you spent a little bit of time working with arithmetic sequences, and now we're going to work with something very similar called geometric sequences. And we're kind of going to do the same pattern as we did with the arithmetic sequences. We're going to find a recursive definition, and then we're also going to find a closed formula. Alright, so a geometric sequence is a sequence where instead of subtracting each pair to get the same number, now we're going to divide each pair of adjacent terms to give the same number. And as before, I will show you an example to see how that works. So suppose we have a sequence that starts with 2, and whenever we divide a pair of adjacent terms, we get a result of 3. So of course we're going to start with 2. Now we imagine what number do we divide by 2 to get a result of 3? Well, that's 6. 6 divided by 2 is 3. What do we divide by 6 to get an answer of 3? Well, 18 divided by 6 is 3. 54 divided by 18 is 3. And 162 divided by 54 is 3. So, etc. And we don't just have to divide by whole numbers. We could divide by any real number. So let's say we divide by 1/2. That'll be fun, dividing by a fraction. So let's see, if we start with 12, say, we want a number where we divide by 1/2 to get 12. Now remember, dividing by 1/2 is the same as multiplying by 2. So we want the number 6, because 6 times 2 is 12. That means 6 divided by 1/2 is 12. And then if I want to ask myself, well, what do I divide by 6 to get 1/2? 3 divided by 6 is 1/2. 3/2 divided by 3 is 1/2. 3/4 divided by 3/2 is 1/2, etc. Another way of looking at geometric sequences, and you can kind of see it in the examples that we gave, you can start with a number, and to get to the next term, you can keep multiplying by the same number. So when we went from 2 to 6, we thought of that as 6 divided by 2 is 3. We could also have thought about that as 2 times 3 is 6, then 6 times 3 is 18, etc. So let's use this kind of reasoning to make a recursive definition of a geometric sequence. So let's look at our old friend 2, 6, 18, 54, etc. So we're going to start with 2 as our first term, and then multiply by 3 to get each term after that. So if we think of the next term as being a sub n, we can think of the current term as being a sub n minus 1, because that comes right before the next term. And then what we're saying is we always multiply the current term by 3 to get to the next term. So if I take the current term, a n minus 1, and multiply that by 3, that's what we get there. We should get that equal to the next term, which is a n. And then we can turn it around to make it look a little prettier. A n equals 3 times a n minus 1. And remember, this formula only works for n greater than or equal to 1, because if we use n equals 0, we get 3 times a sub negative 1, and there's no negative 1 term. So we do have to have an a sub 0, though, but we can just define what that is. So we'll just say a0 equals 2, a n equals 3 times a to the sub n minus 1, when n is greater than or equal to 1. So now let's use kind of similar reasoning as we did with arithmetic sequences to find a closed formula for geometric sequences. Once again, we're going to look for patterns to figure out what that formula is. We're going to act a little bit stupid to do it, right? But in a smart way. So here's our sequence. Our first one is 2. Our second one, well, how do I get from each term to the next one? You multiply by 3, so our next one is going to be 2 times 3. And instead of being a smarty pants and saying that's equal to 6, we're just going to leave it as 2 times 3. To get to the next one, we multiply by 3 again. To get to the next one, we multiply by 3 again. Already, you're probably seeing a pattern for a sub n. If you're at a sub 1, you take 2 and multiply it by 1 factor of 3. If it's a sub 2, you take 2 and multiply it by 2 factors of 3. A sub 3, you take 2 and multiply it by 3 factors of 3. So for a n, you take 2 and multiply it by n factors of 3. So multiply it by 3 n times. So our a sub n is 2 times 3 to the n. Alright, so now that you've sort of got your head around geometric sequences, you can go ahead and finish the activities for arithmetic and geometric sequences.